Hey everyone, and welcome to this explainer. If you've ever found yourself wondering how artificial intelligence actually learns, well, you are in the exact right place today. We're going to unpack the mathematical beating heart of machine learning, which is vector calculus. The core premise we're looking at is that machine learning is, at its foundation, just a massive, mind-bendingly complex optimization problem. And the engine driving that optimization? It's vector calculus. By the end of our time together, you'll see exactly how these algorithms can navigate through literally billions of data points to land on the perfect solution.
Here is our quick roadmap for today. First, the engine of optimization. Second, partial derivatives and gradients. Third, mastering the chain rule. Fourth, Jacobians from multiple dimensions. And finally, number 5, Hessians, measuring the curvature.
All right, let's jump right into section 1, the engine of optimization. So at its absolute core, optimization is just the process of finding the best possible model parameters. We're talking specifically about things like weights and biases, and we want to tweak them to minimize a specific objective function. Now, you can think of an objective function simply as an error rate in a neural network. Obviously, we want that error to be as close to zero as humanly possible, right? Imagine you're dropped into a vast, pitch-black, multi-dimensional mountain range. Your one and only goal is to find the absolute lowest point in that entire landscape, the bottom of the deepest valley, because that lowest point represents the lowest possible error for your model. Finding that spot, that's what optimization is all about.
Moving on to section 2, partial derivatives and gradients.
So here's the problem. How do you find the bottom of a valley when it's pitch dark? Well, you need a compass, a mathematical compass. In standard high school calculus, a basic 1D derivative measures a simple slope with respect to a single variable. If you take a step forward, do you go up or do you go down? Pretty straightforward. But in machine learning, our models don't just have one variable. They have millions, sometimes billions of them. That's where the multivariate gradient steps in to act as our compass. Instead of just giving us a single number, the gradient is a vector. It's a whole collection of what we call partial derivatives. A partial derivative basically just asks, hey, if I change this one specific parameter but hold all the other millions of parameters perfectly constant, how does my error change? By collecting all of those partial derivatives together into one single vector, we get a compass that points precisely in the direction of the steepest descent up our error mountain.
Geometrically speaking, the gradient generalizes that simple derivative to functions of several variables, and it always points orthogonal, so at a right angle, to the function's contour lines. Now, since the gradient points towards the steepest way up, and our whole goal is to minimize our error, we obviously want to go down. Because of this, gradient descent algorithms intentionally exploit the math by moving in the exact opposite direction, the negative gradient direction. By taking iterative, calculated steps in that negative direction, the algorithm actively and efficiently hikes down the error surface right toward that minimum valley.
Which brings us to section 3, mastering the chain rule.
Now, finding that gradient sounds simple enough in theory, but there's a massive structural catch when we get into deep learning. Neural networks aren't simple. They're composed of layers upon layers of functions, all nested inside of one another. Kind of like a set of mathematical Russian nesting dolls, where the output of one layer immediately becomes the input of the next. Mathematically, we write this as a nested function, like h of x equals g of f of x. To find the derivative of this entire stack structure, we have to use the chain rule. The chain rule tells us to take the derivative of the outside function and multiply it by the derivative of the inside function. It basically recursively unpacks those layers, which is absolutely crucial because it lets us calculate how a ridiculously tiny change in a weight in the very first layer ultimately ripples through and impacts the final error at the very end of the network.
In actual practice, we apply this using a computation graph. You see, in machine learning, we don't try to sit down and write out one gigantic, impossible-to-solve equation for the gradient. Instead, we use a really elegant process called auto-differentiation, specifically the reverse mode. You probably know it by its universal name, backpropagation. What we do is start at the final error output on the right side of the network, and we pass our mathematical compass backward through the graph, going node by node. We multiply the local gradients together, accumulating the total gradient as we move backwards. This is the exact algorithm that makes training deep, multi-layer neural networks computationally possible. It's a total game changer.
Let's move to section 4, Jacobians for multiple dimensions.
Okay, let's add another layer of complexity here. What happens when a function doesn't just output a single number, but spits out an entire vector of numbers? Well, when functions output vectors, our gradient has to level up, transitioning from a simple vector into a matrix. And when we start computing gradients of matrices with respect to other matrices, which, by the way, happens constantly when you're dealing with layers of weights in machine learning, we create these incredibly complex, multidimensional structures called tensors. At this point, we're no longer just tracking a single slope on a hill, we are tracking a massive, dense 3D grid of interacting rates of change. This brings us to the formal definition of this massive collection, which is called the Jacobian. The Jacobian matrix, or tensor, depending on the dimensions, collects all the first-order partial derivatives of a vector-valued function. When you're dealing with matrices being mapped to other matrices, the size of this Jacobian explodes into some pretty massive tensor sizes. But it's super important, because the Jacobian allows the algorithm to track exactly how every single element of an output matrix shifts in response to a change in every single element of an input matrix, all at the exact same time.
Now, if the idea of calculating gradients across four-dimensional tensors sounds computationally terrifying to you, trust me, you are not alone. But thankfully, mathematicians use a brilliant and honestly pretty simple trick called flattening. Because matrices represent linear mappings, we can systematically reshape or flatten our matrices out into really long vectors. This incredible little transformation actually converts all that complex tensor calculus right back into standard, manageable matrix multiplication. And that is exactly what keeps the math running so fast and efficiently inside your computer's GPU.
Finally, Section 5, Hessians, measuring the curvature.
So we've got our compass, and we can handle multiple dimensions. We're good, right? Well, standard gradient descent actually has a bit of a blind spot. It only knows the slope. It doesn't know the actual shape of the terrain. If the gradient is a first-order derivative that tells us the slope, the Hessian brings in second-order partial derivatives. Here's how it works in steps. First, we calculate our standard first-order gradients just to find which way is down. Step 2, we calculate the derivative of the derivative. Doing this builds the Hessian matrix. By calculating how the slope itself is changing, we extract some really critical topographical data. Then finally, step 3, we use this advanced local curvature data to train our network significantly faster. We can take smarter, much more calibrated steps down the mountain.
The true power of the Hessian lies in the fact that it's a symmetric matrix, mapping out the local curvature of our error bowl. Why does curvature matter? Well, think about it. If you only know the slope is really steep, you might take a massive step and accidentally overshoot the bottom of the valley entirely, literally bouncing right up the other side. By knowing the curvature, those second-order properties we just talked about, the algorithm knows exactly when the valley is starting to level out. The Hessian effectively acts like a set of brakes on a car, allowing for highly intelligent, non-linear optimization that hones right in on the minimum without overshooting it.
To wrap up our journey today, consider this great summary from the source text by Dyson-Roth, Feisel, and Ong. Gradient descent exploits the fact that a function decreases fastest if one moves in the direction of the negative gradient. It's just such an elegant summary of a vastly complex system. Whether we're dealing with a simple linear regression or those massive billion-parameter deep neural networks, these specific tools we covered today, the partial derivatives, the chain rule, Jacobians, and Hessians, they truly form the undisputed fundamental engine of modern machine learning. They take the seemingly impossible task of blind optimization and turn it into a precise mathematical science. But as we close out this explainer, I do want to leave you with a quick thought about the horizon. We've mapped out the mathematical engine that built the AI of today. But as models move beyond mere pattern recognition and start moving toward true reasoning, you have to wonder, if gradients and Hessians solve the optimization problems of today, what entirely new mathematical architectures are going to be required to optimize the artificial general intelligence of tomorrow? It's something to think about. Thank you so much for exploring this with me today. And as always, keep questioning the math behind the machine.